Lab 2, Motion of a Falling Object. The purpose of this lab is to observe the motion of a free-falling object from its initial position, which is at rest, and to do so, we'll be observing two models using tracker, one considering only gravity and one considering gravity and the force of drag. To understand this motion, we will be using Newton's second law, and we know that there is not a constant velocity with a free-falling object, which leads us to the statement that the net force does not equal zero because there is a change in the velocity. The net force in the y direction is equal to the force of gravity plus the force of drag. The force of drag equation is when drag is proportional to velocity squared. Here is the experimental setup. Here's the video I took and uploaded into Tracker to analyze. And you can see the graph in the top right corner has a nice concave shape showing that there's an increase in the position as the time changes, which means there's a change in the velocity of a falling ball. Here is the observed data put into GlowScript, with only observing gravity, which is labeled as predicted position on the next slide. In GlowScript, I put g is equal to 9.8 and change the unit vector for the position on the y-axis to be j hat is equal to vector 0, 1, 0, and then change the net force equation to equal W, and set W to equal negative mass times gravity times j hat, which is the weight force on the system. I then used the position update formula and the velocity update formula to find how the ball changes velocity and position in each frame. And then for this model, we are only observing gravity with the arrows and no other forces. And it has a constant velocity because only gravity is impacting this. As we see in the plotted data points, the observed and predicted data do not line up, and this is because of drag force. The predicted data is falling a lot faster than the observed data, so to account for this key difference, we'll go back into GlowScript and add in drag force. We need to observe the force of drag because if we create a free body diagram to show the forces acting upon the ball while it is in motion, we would have both gravity and drag acting on it as seen in the picture above. Here is the GlowScript in which we added in drag. You can also see we added in b equals 0.17, while in the previous GlowScript b equaled 0. We also added in arrows to show drag and gravity, which you can see in the video. As you see, drag has a smaller arrow than gravity, and it is because we have not reached terminal velocity, where the force of gravity would equal the force of drag, which creates zero net force. We can observe this will happen eventually on the graph of time versus velocity. Now, the graph of observed data and the predicted data containing both the force of gravity and drag are much more similar to each other with their concave shape. Any errors that occur now are most likely from Tracker and the improper placement of the points to the center of the ball. So what does this mean? The slope of the three graphed lines show an increasing polynomial trend in the negative direction, and this is due to the force of gravity, which has a constant, which is negative 9.8 meters per second squared. To predict terminal velocity, we would set the drag force equation equal to the weight force and solve for its velocity. The terminal velocity can be seen in the graph of velocity versus time, where the line will level off and becomes constant because there is no net force. This did not occur in any of my graphs, which you can see in the picture above. In our lab, the first graph of predicted position only shows the force of gravity, and its velocity versus time graph was constant, as shown on the left. In order for the ball to have reached terminal velocity, the velocity must be different at each time interval and eventually level off to have a more convex shape. I believe that to show terminal velocity for my experiment, I would need to drop it for a longer amount of time, because even on Tracker, the ball fell at an almost constant velocity as shown in the graph on the right. What if? If the ball was initially thrown downward, then the ball would have an initial velocity, unlike in our experiment, where the initial velocity was 0 because it started at rest. The ball would reach its terminal velocity in a short period of time, and this is because it would require less time to accelerate to reach its terminal velocity, and this can be seen in a graph of velocity versus time, because the line will eventually level off and become constant, and this is because there is no net force. On the graph of the object thrown would level off much quicker than the ball dropped, and this is due to the velocity update formula, since the final velocity, net force, and mass would all be constants. and the initial velocity would be the value that changes over time. And time is inversely proportional to initial velocity. Thank you.